to the defects that you just saw in this little video. So this can actually be understood very simple by just writing down a tight binding model. You write down a tight binding model in which you have a unit cell with just two sites in it, which are just two carbon atoms. And then you have either strong bonds or weak bonds. And this would be like the double bonds and the single bonds. We can just translate this into hopping strengths of electrons between these individual carbon atoms. So you would then figure out the band structure by writing down a 2x2 Bloch Hamiltonian, which has two eigenvalues at every value of k. And this then forms two bands. They are separated by a gap. This is related to the difference of the strengths here. It is also symmetric in the simplest approximation, where you think that all these carbon atoms are chemically identical. So the only thing which changes and differs are these strengths. So there's some symmetries. It's known as a carbon symmetry. And the defect would be looking a little bit like fusing an additional atom into the system, forcing it somewhere into the middle so that you disrupt this dimerization pattern. And then it gives rise to these topological states. Now, for this talk, there will be actually three things which are important about these topological states. One is that they are sitting at zero energy. The symmetries in the system allow it to only sit at this place. Then the states are decaying exponentially. This is essentially sitting in the band gap. Outside in the bands, there are no available states. So they're like evanescent states that are decaying into the bulk away from this defect. And what is also important is that they're only sitting on one of the two types of atoms. I said they're all chemically identical in the sense of like looking at the individual atom, but if you want to write down this unit cell, you can distinguish red and blue dots. The red dots have the strong bond to the pointing to the right, the blue dots into the other direction. So just geometrically, they are distinct. And you see that the atom which I fused in there, which I forced in there, is a red atom. And this is actually reflected by some rule in this state. This state is an extra state in the system, and all of its weight needs to be distributed then across the red sublattice. This will be quite important. Now, when we transfer these things from, say, electronic systems to photonic systems, there are also some noticeable differences. And they actually make this game much more interesting. So for photons or phonons, at some level, we don't have conservation of charge. So these are actually bosons. We can manipulate them in other ways. There will be gain and loss. And then we will have complex energies. We will have non-orthogonal modes, the things that you very intimately relate to non-Hermitian physics. But there are also two other things which I just mentioned for completeness. In the electronic realm, we always work above the Fermi sea. That's very important to stabilize these topological excitations so that they cannot dissipate and decay. So they actually are particles. And they are particles for a second reason, because they can also move. So when we have topological defects in electrons, they say this dimerization pattern which we have here, this can actually change. One of these two electrons in this double bond can hop over here, and then you would have two weak bonds over there. So these defects can change and they become real particles, quasi-particles with unconventional characteristics like no spin, but half of an electronic charge. These kind of effects appear on this level. But it's a bit more difficult to see how these aspects would transfer to other platforms. So we have some new things on other platforms, and we have some things that we are missing, and we might want to replace by other effects because they actually are desirable. And on a more fundamental level, we have to understand whether these are then actually really still, for instance, topological systems. So we need to go back and look at the reasons why these systems were robust in the first place in one platform. Now, what I want to advocate throughout the rest of this talk is that we can just take guidance from physical signatures, and that there is a general framework in which we can write some rules or link observations to these features and even figure out whether they are topological or what is a non-Hermitian aspect. And this is something which is much broader. It is not just related to topology and non-Hermitian systems, and it is actually unifying physics in a way that we actually know from what we learn at undergraduate level. Okay, and the keyword that we will be using in many different settings and many examples, and I will have to skip over some, I already know this, is response. So we can study the response of these systems. And this is actually something which people did from the very beginning in these fields. So when people were studying these electronic topological systems, one question that they were interested in is how do the systems respond when we break the symmetry that makes them robust? And in this setting here with this carbon chain, you would just make these two carbon atoms chemically non-equivalent. So you actually give them different on-site energies, a plus delta and a minus delta. What this does is actually not to break the symmetry of the band structure. The extended bands, if you look at the range of the extended bands going up here, so there's a bottom of the band and then it goes up, there's a certain range. This gap will just broaden. For the extended states, the symmetry will still be the same, just in terms of energies. But if you follow the defect state, it will actually still sit only on this red sublattice. So exactly, it will remain a solution and its energy will change, but in a predictable way. Namely, it will just move from 0 to delta. So as a function of delta, you see something which doesn't look symmetric in this diagram. What I mean is what is missing is an equivalent line going down with minus delta. This state just doesn't exist in the system. So by probing the system, actually by breaking the symmetry, by looking at the response to different types of fields, you can distinguish the normal states in the system, the topological states in the system. And we know that this is a common thing that we actually already exploit. For instance, when we say, well, this delta that could appear in a different context, maybe in a larger Bloch Hamiltonian, our matrix element also depends on different directions. And so there will be a dispersion relation, a band structure in these other directions. Only at a certain point in the band structure, our system has these symmetries. Away from it, the energies change, but they change in a predictable way, informed by what happens at the symmetrical point. And this could mean that, for instance, this energy changes as a function of a wave number in this same way. And now what this means is that the group velocity will be positive. So there's a state which is moving into one particular direction, like at the edge of a quantum Hall bar. There is no state that is moving into the other direction. So this idea of looking at the response, perturbative or beyond, is a very powerful idea to just probe these systems. So I'm just going to start out the actual talk by showing you a photonic manifestation of this idea, where we already twist this idea a little bit. And I call this topological mode selection. The idea is to take a system which has the same structure. Mathematically, it's going to describe in a very similar way, only that we think of it of a photonic system, which gives us some more freedom to write down the Hamiltonian. Namely, we can make the on-site potentials complex and in particularly imaginary. What this models, if you just look at the conservation laws, when we derive the continuity equation for the Schrödinger equation of our tight binding model, it actually generates photons or destroys photons. So this is just describing gain and loss in the system. And when we want to use this to try and break some symmetries, we would just give different rates of gain and loss to the blue and the red sublattice. Now, what's going to change is actually not so much again to the extended states. If I look at just the real parts of all the energies, the real parts of the energies don't really seem to be affected by too much. In this case, actually, the gap becomes a little bit smaller, but the symmetry of these states will be preserved. The real part of the energy of this defect state also doesn't change, because we didn't really do anything to the real parts of the Hamiltonian. What we have to do is to go into the complex plane. Then these bands here from the extended states, they will project onto lines, like continuous lines at a given height with a fixed imaginary part. And this is just the average gain and loss that we put into the system. And then we have this topological state, and this will again be different energetically, but now in its imaginary part, because it only sees again what we put onto the red sublattice. And therefore it will just see the rate amplification or absorption rate on this sublattice. Why do I call this topological mode selection? Well, this is a topological mode we have selected in the following way. This is now the state which has the longest lifetime in our system. Because these imaginary parts of these energies, if you just put them into the typical exponents multiplied by I times t, that translates into different decay rates and amplification rates of these states. And now we have a tool to manipulate this state, its relative lifetime with respect to all the others, and for instance can make this a lasing state when we have some nonlinear medium and some feedback. And so this mid-gap state is selectively amplified because we broke this sublattice symmetry in the same way as people probe anomalous response in electronic systems. I will tell you very soon that there's another symmetry which is left, which actually guarantees us that this frequency, the real part of the frequency, doesn't change. At this level, we have broken one of the symmetries. So this actually has been realized already quite a while in different platforms quite a while ago. And the first one was micro-resonators, where you just took little resonators. They are about a few millimeters large, really just like I show here. The whole experiment is probably this, a bit larger than I can show on the screen. But it's actually amazing when you see it sitting on the table. It looks very innocent. And it is very innocent. Every resonator just takes a single mode in a certain frequency window. They're spaced out with different spacings, which gives you the different coupling strengths. People can put little gray elastomer patches, which put a little bit more absorption on every second side. At the middle, you have a defect in the spacings. So there are two wider spacings. And then you have antenna, microwave antenna to excite the system and other antennas to pick up the signal. You actually put another plate on top of it so that is not so much signal is getting lost. And then you get these kind of densities of states. This is frequency. This is the response of the system. And this is the situation without the defect and without the losses. I just show that you get size quantization. These are 20 resonators in that case, and you get 10 peaks coming from the valence band, essentially, and 10 peaks coming from the conductance band, so just discretized spectrum. Then you put this extra resonator into the middle with wider spacings, and you find an extra peak. And this is sitting now not at zero frequency, but at the frequency of an isolated bare resonator, which is really the zero frequency in this picture. And then we can put in these extra losses, and you see that this just becomes the most visible peak. All the other states, they see some of these losses and get broadened and suppressed. They actually also get a bit shifted. The symmetries are broken in some ways. This is an experiment. There are no fundamental symmetries at play, but they're still good enough as long as these states don't move into this region here. This zero mode survives, it is selected, and actually its width and its height doesn't change at all. And there I have to trust the experimentalists. They promised to me, they looked very carefully, that nothing changes with this state, which I found quite fascinating. These kind of systems, they can also then be extended. This whole idea, whenever you have a system with two sublattices and a certain coupling configuration, you can extend this. And I just show you very briefly how this extends to different situations. For instance, you could have a system which is essentially like a square lattice with some sides missing. It's called a leap lattice. Now, even without the edges, just in the bulk, if you just write down the Bloch Hamiltonian, you have a 3x3 matrix. And now you have already two red sides and one blue side in there. So this has the same symmetry without any further assumptions if you just have nearest neighbor couplings. So now already in the Bloch Hamiltonian, just by energetic symmetries, there must be one state which has zero energy for every value of k, which we call a flat band. And this flat band will also only sit in terms of its weight, the wave function, only on this red sublattice. Now what we can do is again play around with the couplings to isolate the state. And the first thing is to shift these resonators a little bit so that we have alternating spacings up to a point in the middle where we have wide spacing around the defect. So the alternating spacings in the bulk, they just open a gap, similar to like in the SSH model, the Sushri-Fajeda model as it is called, which I showed you before. You open up a gap. Now this wider spacings, they isolate a state. And now if you look very carefully, this is a blue state. It's living on the other sublattice. And now there's something in this experiment which actually helps us a little bit. There are some additional couplings between the red sides because they really can see each other. The blue sides are in the shadow after a red side. But these red sides, they see each other a little bit. So a little bit of the symmetries are broken again, but in a favorable way, so that we actually get a little bit of spectral separation in there. And then you can see this again in the experiments and put in gain and loss and isolate them nicely. But that's exactly the same principle which I showed you. So if you want to see more of this, just rewind later on when you go back to the video and look at the details here. And similarly for this experiment, for exciton polaritons, so you can push this further into more complex systems which have strong linearities, like these exciton polaritons. They also have more bands, and I just want to say that you can do similar things on different platforms. So this mode selection is actually very transferable. The original idea was actually to use this to build a laser. And again, just to flash this up very briefly, this actually has been done on many different types of laser devices. And this is just one where I was involved with as a collaborator. So in the group of Yang Feng, he did beautiful experiments already in the past with, again, some ring resonators, which are just spaced out in different ways. And then he built two different devices, one in which he had 9 of these resonators with a defect already in the middle, and another one in which he also put losses on every second resonator. Now, without the extra losses, this is actually a very bad laser, because it's very hard to fabricate all these rings so that they're identical. And because of the additional nonlinearities, they will a little bit detuned and they start to become independent lasers. So they laser at different frequencies, and it is not a really nice laser. But if you put in these additional losses, so you pump the system at the same strength, but you put in some additional losses, it actually becomes a better laser. So even the peak intensity becomes larger, everything goes into one peak. And this is exactly this topological mode selection in a more complicated setting, because, for instance, also nonlinearities would play a role. I'm not going to talk about nonlinearities in this talk, but if you have questions, I can talk about nonlinearities and what happens to all these effects, which we really like to see in nonlinear systems. Okay, so this was a very concrete effect, and we make use of some symmetries that we already knew of from the electronic setting, and we used gain and loss. But there is certainly more to this picture. So what is actually still topological if you have systems with gain and loss? And I give you a very limited perspective on this, just to give you some background of the symmetries that we are usually talking about. So the symmetries that people use in the electronic context in order to classify topological matter are principally 3. One is time reversal symmetry, and this is just sending a particle moving in one way back, but it preserves the energy of this particle. Now we encountered some symmetries between opposite energies, and the symmetry that we encountered there is really the chiral symmetry. Because if you go from one point to another point down at the same value of k, you see that the band structures, they're slanted in opposite ways. You also send the particles back. This means that this chiral symmetry takes a particle at one energy to the particle at the negative of that energy, but also moving in the other way around. And if you combine these two, you get a symmetry which is sometimes called particle hole symmetry and sometimes called the charge conjugation symmetry. And I use usually C because P often means parity time, the P in parity in the context of non-Hermitian physics. So this charge conjugation symmetry, this is just the product of these two, and it actually takes a particle at one energy and sends it in the same direction, but at the negative energy. So mathematically, often we think of the time reversal symmetry as a complex conjugation. The chiral symmetry puts a minus sign in front of the Hamiltonian, And the combination is just really the mathematical combination of these things. And in optics, all of the three things are actually realized. So PT symmetry in a certain basis, parity time symmetry, is just a system which has an effective time reversal symmetry. But what it means in a non-Hermitian spectrum, it means you have complex energies which are either real or they occur in complex conjugated pairs, which is really based to effectively the Hamiltonian being real. Okay. Now there is this thing here in optics turned out to be called supersymmetry, because there is a different link between chirosymmetry and what people call supersymmetry. But what it means in terms of the facility to get some protected states, this will now be in the complex plane a symmetry around the origin. So there might be some states sitting at the origin and they would be protected by this symmetry. And what we actually encountered just before in this little example is called the charge conjugation symmetry. And this allows us to slice states up and down the imaginary axis, but it doesn't allow us to deviate to the right or the left. The only thing that we can have are pairs which are already sitting there, and then there will be bifurcations, exceptional points, which actually result in phase transitions. Okay, so just to briefly explain parity time symmetry, as I mentioned, and supersymmetry, these are things that were already known, but this time reversal symmetry can be broken other ways, so you have other topological lasers. But in the example which I showed you, this arises in a very simple way. We have two sublattices that are just coupled to each other, but not directly. There's no coupling from blue to blue. So these are these off-diagonal blocks. And the only thing that happens in the blue subsector are on-side terms which are imaginary, and the same in the red sector. And then you can show that you can use the Pauli Z matrix to put minus signs in front of these terms, and the complex conjugation to put minus signs in front of these terms. So this system actually now realizes a non-Hermitian version of this charge conjugation symmetry. And this all works fine even in terms of topological quantum numbers. You can define winding numbers and see that these states have some topological meaning. But at some point this will actually break down. And this breaks down when the band structure, when the gap closes, which you can achieve by tuning up the gain and the loss in the system. So there's definitely more in these systems than what I've told you so far. So let's look at some further complications from gain and loss. So, and let's look at the mathematical structure of these degeneracies first. I mentioned them already in the non-Hermitian setting. Degeneracies, they're called exceptional points. So I use this word exceptional points already. So they're degeneracies. And what is particular about these degeneracies are two things. One, it is just the analytical structure, that the energies depart much more violently from each other than in a Hermitian system when you go away, namely as a square root instead of just linearly. This is something that you can see in perturbation theory. And there's another aspect which is related to the eigenmodes, which are actually collapsing. So let's have a brief look at the consequences of this in the context of what I've told you already. So first of all, these can appear in the band structure. And this is a very simple example of a system in which we have resonators again. It translates to this tight binding chain. And if you just look at what makes the system non-Hermitian is now not imaginary parts, but different values of A and B. So this matrix is no longer symmetric. And if you make A and B sufficiently different from each other, you change the band structure, you get a phase diagram. And what happens is that you get branches in which the band structure is completely real or it is completely imaginary. And at the values of K where this changes, you have an exceptional point. So a degeneracy where two states meet and two real energies go into the complex plane. Okay. And the problem that you have is that this actually also gives rise to protected states that you would not expect in the original electronic setting. So we can take such a chain, we can look at a table, we can say that with the symmetries that we have, there are no protected defect states, or no defect states actually at all, appearing when we would couple them together. But we can couple them together in a very simple way by just reflecting half of them, work out the spectrum in a finite system, and we find that these states actually exist. And indeed, they are going to be born in exceptional points. So at certain points, when you change parameters, states appear on the real axis, and then they disappear on the imaginary axis. And there will actually be 4 states of these. And you can characterize them again with some winding numbers in a more complicated way, but you find new states. So this breaks the topological classification of the systems. And there are other classifications nowadays, but personally, I always find that the exceptional points become much more important, because almost everywhere now you can find these states. So what you should really do is to shift your focus and study the exceptional points much more. And the main question that you should ask is how your exceptional points are, for instance, constrained. And I know Flora is probably listening, and she had a very nice paper recently on symmetry-constrained exceptional points. Okay, so what is exceptional, or what is interesting about these things, is there are things that don't happen if you just make a system slightly non-Hermitian. If you make it slightly non-Hermitian, you can still extend your Hermitian knowledge a little bit. And then suddenly, drastically, something changes, and new states and new physics appears. Okay, so how can we see this in the response of systems? And the first place where people looked traditionally was actually in, again, the response to perturbations. So very similar to what I told you before. So I give you first the general picture that is already well established, and then I tell you some new things about this aspect as well. And this is all related to this non-orthogonality of states. So in a Hermitian system, when you have 2 eigenstates, they are orthogonal to each other, or even if they're degenerate, you can make them so. In the non-Hermitian case, you have to distinguish 2 types of states, the so-called right and the left eigenstates. And the left eigenstates are mathematically orthogonal to the right eigenstates, but within each set, you don't have this orthogonality feature. And now you can make different choices, but for instance, you could normalize the right eigenstates, and what you will find is that the left eigenstates then have to typically be longer. They cannot be unit vectors anymore. And you can measure this by the length of these states. It gives you an indication of how non-Hermitian this system is based on this kind of feature. So this is mathematically a condition number. Physically, it's called the Peterman factor, and I'll show you very soon what this Peterman factor does actually in the physical world. You can generalize it in a way so that it doesn't really rely on your choices of normalization. So this is still just the condition number in this context, and it's generally larger than 1. And it shows up directly in perturbation theory. So if you do perturbation theory, you know you need to project. You need to project your perturbation out. And in first order perturbation theory, you just take your state and you multiply it from the right and the left to your perturbation, and you use normalization to figure out by how much an eigenvalue changes. And if you want to do this correctly, so that you project out the correct piece, you need to use some vectors which are orthogonal to the vectors that you used in your first step, so the left eigenvectors. And then if you take some generic perturbation and just think how large is this thing typically, you see that, well, typically there is a matrix element. I'm a mesoscopic physicist. For me, everything are energy and time and length scales. Before you do a calculation, you try to figure out these. And these actually change if you do it in the non-Hermitian system, and they're just getting multiplied by this Peterman factor. And that can completely change the picture of your physical system. So this directly enhances the sensitivity to perturbation. And now these things become very large when you go close to a degeneracy. So as you go close to a non-Hermitian degeneracy, also these vectors actually become the same. And then you get a problem that you cannot really even define a complete system of eigenstates at the exceptional point. And as you approach this Peterman factor or condition number, it actually diverges. Now, this is quite well known in quantum optics. Before, in quantum optics, when people were building lasers from the late 1970s, they were interested to really find out the quantum limit of the laser line width, and they realized that this is important. And that's where the name Peterman actually appears first. He was a person interested in semiconductor lasers, which were leaky to the sides, and wrote a theory paper. And at the time, he actually said, He has written this paper, but he doesn't believe it until there is an experiment, because it sounded so unbelievable that something which is essentially related to the uncertainty relation can change because you open up your system. But there were experiments, beautiful experiments in the 1990s. Now, when we add symmetries to this becomes actually really important for our field. So, for instance, one of the early ideas in PT symmetric optics was to mimic PT symmetric quantum mechanics. That's a version of quantum mechanics in which you lift some of the constraints and you still try to get a consistent theory. And what turns out is that the Peterman factor tells you that you really cannot do this in the optical setting. And the reason is that behind this, there's a Hermitian theory, which is quantum electrodynamics, and there will be noise. And the noise will be very sensitive in this non-Hermitian setting when you have this, when the Peterman factor becomes involved. So I just show you a brief example. It's preparing something which I'll cover 2 more things in the next 10 minutes, just to prepare you a little bit for this. So you can just look at a cavity which has gain on one side and loss on the other side, and it has semi-transparent mirrors that we can close up. And in the limit that these become real mirrors, we want to realize a PT symmetric system. And we want to see whether we can do this consistently. So what happens in this limit is that the complex energies should all move onto the real axis. We want to work in the PT exact phase before we have any complications from exceptional points where the spectrum is already complex, even in the setting. And then we need to do this consistently. We need to think of the individual photons. And we know that they're actually going to be created in individual stochastic processes in the gain medium. And these are not necessarily going to be compensated exactly at the right time by a lossy process, by an absorption process. In order to figure out whether this is important, we just use standard quantum optics tools. And I always use the scattering matrix for this, because there's a thing which is called the input-output formalism, and it just cuts straight to the result, essentially. So we use the scattering matrix, we implement some symmetries, which again involve complex conjugation and some Pauli matrices. And then we work out a consistent theory, and we work out how much of intensity is actually leaking out of the system. And we find that this is actually going to be multiplied by a large number, which is related to these condition numbers. So this actually doesn't work. The system actually builds up infinite radiation intensity inside, so that there's always finite intensity going to the outside, and there's a conservation law behind it, which just means that the overall theory, including the environment, is a consistent quantum theory. Now we can actually take the same system and steer it to this exceptional point, and we see that this even becomes worse. What happens is that you have 2 isolated peaks. They get closer to each other, and the intensity is going to increase even further. And at the exceptional point, I don't even put the scale, it's very large, but it's still finite. So the Peterman factor at this point actually diverges. But it diverges because we are no longer using the right way to try to analyze our signal. What changes from this point to this point is that instead of having Lorentzians to which we can fit our signal, we get a different line shape, namely the square of a Lorentzian. So fortunately, nothing diverges in physics. Even so, some mathematical quantities like the Peterman factor might diverge at the exceptional point. It indicates something, and something that we can also measure, but it indicates something that we first have to figure out. And in this case, it is the change of the line shape. So it can actually be seen very quickly why this arises, because the actual structure of the scattering matrix is a product of 2 terms, which we try to artificially separate into 2 Lorentzians, with a minus sign, which is related to a topological phase, the Berry phase of exceptional points. And in order to write it in this forced way, we have to multiply it by a diverging number. Nothing diverges on this side when we make these 2 frequencies the same, but trying to interpret it as Lorentzians is not the right way. So this thing here looks then like this diverging Peterman factor. Okay, so this actually has been seen in experiments. This change of the line shape just about 2 years ago. Right, but in order to understand this really, we should now step back and develop consistent response theory for this. So this will be the last part of my talk. I'm going to show you another example in which we can work out something explicitly and see another effect. And then I'm going to discuss very briefly why we might not always see the things that I told you, because we might need to make our systems complicated enough, or our probes complicated enough. And this is really the value of this perspective of trying to see what happens in the physical response of systems. We see that there's mathematics, exceptional points, then the effects, but we first have to work them out. And this response theory is a really nice umbrella in order to capture everything. So this is just one of 3 detection paradigms, but it's really the most fundamental one. When we just think of the Hamiltonian, we think of spectroscopy. But even in spectroscopy, for instance, we have line widths. We don't just see the Hamiltonian, we see the eigenvalues. We also know that the imaginary parts have something to do with the width, but we also see other parts from the wave functions, for instance. And we can study them separately, obviously, but in order to see how this exactly combines, the Hamiltonian is actually not enough. You look at the spectral response function, which is related to a Green's function. Similarly, when I mentioned the scattering matrix is just another way to probe your system by sending in particles from one side and see how they come out again. But on the bottom of writing down a scattering matrix, there will be a Green's function. And when we generically drive a system, even without putting something in, by just wiggling at a certain point, again, we will encounter the Green's function. And this is actually what we really do. If you looked at this video back, you see you have the finger exciting the system, and then you look what's actually going to happen. So this is a typical response experiment. And you should now wonder, how do we actually read off the wave functions and the energies in this setting? And by how strong does our system actually respond when we do certain things to different parts of the system, just as we see here. And now, what is the role of symmetries? In our setting, in particularly, often things happen when we broke time reversal symmetry. In optics, this is related to reciprocity and makes the game very simple. Namely, it tells us that this quality of a system as a source is the same as a detector, something that you might have heard about loudspeakers, right? Loudspeakers emit sound, but they could also be used to record sound in the same way, because acoustic waves are reciprocal. So what happens in non-reciprocal systems? We have to be general enough in order to capture this. And the thing that actually makes the discussion complicated is the non-Hermitian skin effect. So even in the bulk, now states can become distorted to the sides, even all of the states, because we can have non-reciprocal couplings in our system. And this changes the band structure in a way, for instance, that there is no nice correspondence between the bulk and the edge anymore. You have to work harder to find such correspondences. And I, again, refer to some works of people in the audience in here. Now, this is a very beautiful experiment, which tells us where we have to look and what we have to do. This is robotic metamaterial, which is again excited in the same way by this highly evolved apparatus, many million years of natural development going into this one. And you excite the system in the middle, and you can ask 2 very important questions. First of all, is this actually an edge state? It seems to be distorted to the side, but it could also be just a distorted bulk state. And secondly, what kind of state do you actually see here? Because we know we have right eigenstates, and in most settings, they are actually the visible response, but we also have left eigenstates. So what is the role of the left eigenstates in here? And because I don't have much time, there's a little bit of a calculation that I've prepared, but it's not really important. The left eigenstate is actually just telling us what happens when we move the finger. And we were not to excite the system at this position, but at a different position, because the system will respond in a different way, and we can map this out. So it's actually a very simple calculation. You take your system as driven harmonic oscillators, you drive it harmonically at certain positions, could be a fixed position, could be a combination of positions. You immediately encounter the Green's function, and the right and the left eigenstates. and I'm a little bit frozen. I hope it's not a problem. So you encounter these states. And you can work out the power spectrum, and you will see that it maps out the right and the left eigenstates as a function of frequency and resonator positions. And what you also will see is that there is a phase transition happening, and this is related to the Peterman factor, which also exactly appears in the setting. So we can develop a very general response theory, and it actually will combine all the different aspects that we're interested in. It will combine the spectrum and the wave function, and it will tell us directly what happens to the systems and where we will see phase transitions. And these phase transitions will, for instance, involve this Peterman factor and things that are happening in the spectrum. Okay, that was very brief, I know, but I hope I set the platform for this. So just 2 minutes. My screen is a little bit frozen, Clara. Is that causing a problem on your side?
It looks all good.
Okay, good. Yeah. Then I just continue, and it's really only 2 minutes.
Yeah, you can also take 3 if you like.
Okay, good. Thank you. Good. So what I really want to say is that we should also be a little bit careful sometimes when we discover some effects in the mathematical structure. This step, which I just described, of figuring out the physical response is sometimes really needed so that we can guarantee and make sure that we can see these things, for instance, before we invest a lot of money and time in building an experiment, so that we can see something in the response. And there's a really interesting distinction between passive and active systems in this setting. So in the active systems, the calculation that results in the output of a laser in this input-output formalism actually tells you at the end to take just the scattering matrix and see if it is more than a unitary matrix, a little bit larger because of the gain in the system. And this excess beyond unitarity, which is creation of photons, this actually tells you how much is coming out of the system. In a passive system, this will always be negative by definition. This is the definition of a passive system. It has losses. It might be a neutral system, or it has losses inside. So nothing is coming out, but you can still excite the system and see whether you can see something similar by just exciting it, sending something in, and then collecting it. And now this particular combination here is, however, heavily constrained. So you see this as a thing which has its eigenvalues are constrained in a particular way. And you can relate it to a fundamental object, which is called the time delay operator. In passive systems, we have an additional physical constraint. Namely, nothing can come out of the system before we send something in, while active systems are just emitting radiation on their own. And this thing, which is called causality, helps us to limit and to understand what a passive system can do for us in an experiment. And the story is actually quite simple. This operator, this time delay operator, immediately gives us the density of states. And we now know that it is constrained in certain ways. We can work it out in particular examples. And for instance, we can work it out in the 2 examples that we encountered: exceptional points and the non-Hermitian scaling effects. And all what is important, the only message, the calculation isn't important, is that if we wanted to see in the density of states an exceptional point, in a passive system, what we would see is the merging of two Lorentzians, but we wouldn't see a change of the line width and also no further enhancement. So all of these interesting factors become exactly compensated in a passive system if you work it out in the density of states. And the reason behind it is, in the density of states, right and left eigenstates appear in a balanced way, so that in the passive system, this balance cannot be broken. And so in the density of states, you don't see the enhancement. And actually the experiment, which saw the change of the line width, worked very close to the lasing threshold, and it was therefore using an active medium. So you should not even start to try and do the same thing using the density of states in a passive setting. And the same thing, interestingly, happens to the non-Hermitian skin effect. Again, if you look at the density of states, you might see this in other quantities. You could look into a proper scattering matrix, measuring the whole scattering matrix in some kind of tomography, you will probably find it. But if you look at the density of states, which is really the core quantity in experiments, then you will not see anything. This is a situation where I just plot here the left eigenstates for a certain situation, kind of projected onto some axis. And this is the density of states in the same system as a function of frequency for these open boundary conditions where you see this accumulation, and you see that there is no distortion in the density of states. And it even looks very similar to the periodic system. So the problem of boundary correspondence and the level of the density of states is actually not so severe. Okay, so this is really the last message that I wanted to transmit. There are many other things that we could talk about, but this was not really my plan. So this is just part of a really big picture where you want to end up. You want to make systems more and more complicated, put in non-hermiticity. We would like to develop this to include nonlinearities. We're on the way to include more and more quantum effects. But our ultimate goal would probably be to go to topological quasi-particles. And we are still far away from there. But the main message of this talk is that if you look at the physical signatures of these systems, the mathematical fundaments that we are all interested in get some extra meaning, and they actually sometimes unify features which all look disconnected, especially because in the Green's function, for instance, all these features appear at the same time. You see this in the anomalous response and topological mode selection. It tells you something about phase transitions and how line shapes change at these. It gives you constraints on the observability. And the thing which I skipped is you can use it in order to actually define what an edge state would be in the most general setting. So yeah, I used a lot of my time, I'm sorry, but yeah, I'm hoping for some questions then.
No, that's great. Thank you very much, Henning. I really enjoyed your talk. The floor is open for questions. Maybe I can ask one in the meantime, because I'm still thinking about the Peterman factor. So it's only defined in terms of left and right eigenvectors, right? So would I be able to distinguish regimes of? I can see that I can identify non-reciprocity and reciprocity. But can I also distinguish non-reciprocity and directional amplification with just the Peterman factor? Because you would see it in the Green's function. You would see it different.
Yes.
The Green's function in one case would be, would admit values larger than 1, and in the other case. But you'll be able to see it also from the Peterman factor?
Mm-hmm. So in the system that I studied, the Peterman factor actually diverges in the thermodynamic limit. Mm-hmm. So it is very large. If you take a finite system, you can the phase transition really distinguishes a system in which you have no directed amplification and a system with directed amplification. I really should jump to this slide. And the Peterman factor really diverges in this region. Oops,
yeah, interesting.
Yeah. As you make the system large. And it has a very simple explanation because it's the overlap of the right and the left eigenstates. Now, in the region of directed amplification, actually here we are used for the left eigenstates. They're on the right hand of the system. That's very horrible. But it tells you if you would excite the system on the right, it would respond very strongly on the left. So this is telling you this orange curve here, brownish curve, tells you how strong the system responds, and the bluish one tells you where it responds. And in the amplified directed amplification regime, you excite it on one side and it responds at the other side. And you see that if you make the system larger and larger, these are exponential curves, the overlap becomes smaller and smaller. And the Peterman factor is just the reciprocal of this. So yeah, it exactly tells you it. But it's interesting, it doesn't diverge at these boundaries in parameter space because it's not related to an exceptional point. And I've never seen this before. So it's really a different thing. It's something really related to the wave function flipping over of one individual state and not two eigenstates coming close to each other, a different mechanism. And in order to you need to be careful when we define states in the Hilbert space, we often use this fact of nothing is allowed to exponentially increase into the system. But once we have a bi-orthogonal system, we need to think about it in a different way. And again, Flore knows very much of
Yeah.
to define bi-orthogonal quantization in this context. Yeah.
Yeah, thanks very much. We have one bit more general question on YouTube. Is there an equivalent of many-body localization or Anderson localization in non-Hermitian systems?
There's an equivalent of, then I need to probably tune up my volume a little bit. What were the two terms?
Is there an equivalent of many-body localization or Anderson localization in non-Hermitian systems?
Okay, very good. Yeah, these are two areas of very active research, and one which actually non-Hermitian physics has a long tradition, and it actually appeared in waves. In nuclear physics, even in early random matrix theories, 1950s, 60s, all these things, a lot of the things that we talk about there already appeared, and they just had different names. And then in the 1990s, Hatano Nelson wrote a paper on a system which is very similar to the systems that we are seeing here with directed couplings. So these systems, they are built using directed couplings, and I think it's just my PowerPoint which is frozen a little bit. Sorry. And their motivation was actually then to study Anderson localization. So there's a huge amount of literature, and there is the idea that states delocalize when their energies become complex. So this is one quite general insight. It's not always a strict relation, but this kind of relation exists as a guiding principle. So yeah, so these phase transitions in the spectrum, they can in some cases be related to delocalization transitions. In many body localization, it's a very complicated and unclear picture, because I think we're not right at the place where people are seriously writing down physical quantities. There's a shift towards studying entanglement in these settings. But it's often, you can define the density matrix in two different ways, using the right eigenstates, and it's still Hermitian, or using a combination of right and left eigenstates. And that both of these can be interesting and meaningful and can connect to physics in other areas like conformal field theory. But what you should really do in terms of experiments is completely unknown at the moment. And I think that people like Clara will know it a little better, perhaps from the perspective of open systems theory, where we always work with density matrices. But this is an area where at the moment knowledge is a bit, unfortunately, I would say, spreading into different directions, where we should try to combine it again into a coherent picture. And, very good questions, because these are very active fields of research.
Yeah, thank you very much for going into this one as well. I don't see any more questions at the moment. And since, there is one. If the density of states can't capture the non-emission skin effect, what quantity should one calculate? Here, for example, from the Green's functions.
Yes, some off-diagonal elements, essentially, which translate into off-diagonal elements of the scattering matrix. And so therefore it is essentially seen in transport, and directed amplification is related to this, even though there we think mentally of an active system. The general response there is yes, even those experiments, these robotic metamaterials, they were active systems actually. So but in terms of the mathematics, you see that it's encoded in off-diagonal elements of the scattering matrix, which you can measure. It's however, somehow you need to know more of your system to know. Then there's often, that's actually going back to the earlier question. So you might see it and you know what your system is and you see exactly what you expect, but it's not a proof. And in Anderson localization for light, there was exactly the same problem, because whenever you see something exponentially distorted, is it localization or is it absorption of light? You cannot distinguish these effects. So you, for this particular question, I think the answer is not known. If there is a fundamental way to distinguish in these off-diagonal elements, if they could not just represent something else going on in your system, because we know that normal scattering systems, even reciprocal ones, can have very complicated Fano resonances and all these kind of things. Yeah, open question.
Yeah. Which is good, so more room for research. Well, thank you very much, Henning. I think since we're already a little bit over time, I would really like to thank you again for this very interesting seminar. And I would like to remind you that on the 8th of November, we have another seminar. So watch out for the link, which we'll send by email. And see you then. Thank you very much for joining us, everyone.
Thank you as well. Bye-bye.